So today I'm going to prove that if A is a non-singular and this right here is the Cayley-Hamilton equation. Actually, I misspelled Hamilton. Okay, so looking at this equation and looking at what we have to prove, they look very, very similar. So one thing I noticed is that each one of these terms has a negative in front of it. And looking at these terms, they're all positive. So the first thing I want to bring up is that the properties of zero matrices, and I'm going to paste right in the property I'm using, 2.2 from chapter 2, and especially this property and this property. So this property states that a matrix A added to a zero matrix of the same n by n is going to equal A. So A plus 0 of n equals A. And then this one is the additive inverse. So A plus negative A equals the zero matrix. Okay, so from there, we're gonna take the Cayley-Hamilton equation. And so that's going to be a to the n plus a to the n minus 1. Oops. Forgot my constant. C to the n minus 1, a to the n minus 1, plus dot, 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 plus C2, a squared, plus C1, a, plus C naught times the identity equals zero matrix. That's an N also. Okay, so from here, we're gonna work on this left side of the equation first. So we're gonna take a to the n plus minus a to the n plus c to the n minus 1, a to the n minus 1. Then we're gonna add the negative a to the minus 1 minus or plus dot, 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 minus plus minus dot, 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 plus C2 a squared plus minus C2 a squared plus C1a. Wait a second. Yep. Plus C1a minus or plus minus C1a plus C naught I. And that's going to equal the 0. Well, that's going to be the left side of the equation. So we'll work on the right side in a second. So now if you could tell these terms, so these terms right here is going to equal the zero matrix by n. This is going to equal the zero matrix. So I'm just going to pop that down to 0. These are going to cancel. And this is going to equal to 0. And these are going to equal to 0, which is going to leave just this term on the left side of the equation. So all of this is going to equal C naught I, left side. Okay, so from here, we're going to start dealing with the right side. Since we subtracted on this side, we're going to also subtract on the other side. So let's go ahead and do that. So C naught I is going to equal minus a to the n. And any, I will get into that in a second. And then we're going to, let's get minus c to the n minus 1, a to the n minus 1, minus dot 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 minus c2a squared minus c1a, then plus the 0 matrix. And from that same property that I talked about earlier, anything added to the 0 matrix is always going to be itself. So that's one of the properties of 0 matrices. So from here, we could look at, we're getting close. So, we're looking like we're getting real close. So from here, I'm going to multiply every single term by A inverse. And I can, okay, I'm getting ahead of myself. So we're going to multiply everything, both sides of the equation, by A inverse. So A inverse times C naught I equals A inverse minus A inverse times A to the n. And I'm just going to factor out this minus sign so I don't have to, we'll deal with that later. Minus C to the n minus 1, A to the n minus 1, and A inverse supposed to go right there. Sorry. That's going to be a plus because we factored it out. Plus A inverse dot dot dot. And, that's just still going to be the dot dot dot. So plus C2 A inverse A squared plus C1 A inverse A plus A inverse times 0, and that's going to be 0. So we're looking good here. So we're going to clean this up a little bit. So from here we have C naught, and any matrix multiplied by the identity matrix is always going to be the matrix itself. So again, that is from the definition of in the inverse of a matrix. And I can show you that right with theory I'm using right here. And so from this theorem, an n by n matrix is invertible when there exists an n by n matrix B such that A times B, which is A inverse, equals the identity matrix. So that's why I can multiply that and it's equal to itself. So C naught A inverse equals, get that minus sign outside. So, and this is from the properties of inverse matrices, the properties of exponents. So when two exponents are multiplied by each other, we're going to put a little side note here. Next, I'm going to get a different pen. That was too small. A inverse times A to the squared equals A to the 2 minus 1 So from this is due because of the properties of exponents. So that's going to allow us to deal with these terms right here. So I can combine this to be a to the n minus 1 plus c n minus 1, and that's going to be a to the n minus 2 plus dot 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 plus c2 a. 2 minus 1 is 1 plus c1 times a, these two terms right here, a times a inverse, like I showed you before in the property of inverse matrices, that is going to equal I. So C1 times I. And if you see where we're trying to go here, we're trying to prove this. We are getting very close. So now I'm going to multiply by the opposite of this scalar, C naught. So A inverse C naught A inverse times 1 over C naught equals minus 1 over C naught times all this stuff get rid of one of those minuses. There we go. Okay, so now these two terms cancel, and we're left with the inverse of A equals 1 over C naught. Now I'm going to distribute this negative times minus A to the n minus 1 minus C to the n minus 1 times A to the n minus 2 plus dot 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 plus C2 A. Actually, these are minus. Forgot I distributed. These are dots. Minus C1 I. And as you can tell, I just proved that using the Cayley-Hamilton equation, you can find the inverse of matrix A. And as you can tell, term by term, those are exactly equal. Well, thank you very much.